Welcome back to my channel, and this is the next lecture. From here we'll be doing the conservation and we'll be starting the mechanics of a single particle. We have already done the basic concepts and the major terms which we'll be using while studying the mechanics. So let's move forward, and we'll start with, in the previous last to last lecture we actually left at the conservation theorems, and we did the conservation of mass, conservation of linear momentum, and the conservation of angular momentum. While the conservation of total energy, I gave a sort of homework to all of you, which I hope you must have done it. So let's move forward. So we'll start with conservation of total energy. Now total energy, if I talk, is basically the sum of all sort of energies in a system, like kinetic energy, potential energy, vibrational energy, interaction energy, Coulomb's energy, or any other sort of energy which might be present in a system or in a particle or in a molecule. But while we are dealing with mechanics of a particle, we are only dealing with the dynamics and the statics. Statics means एक पोजीशन के ऊपर जो उसकी वैल्यूज हैं या उसके ऊपर जो इम्पैक्ट्स हैं, एंड डायनामिक मीन्स जो भी उसके अंडर मोशन के ऊपर इम्पैक्ट्स हैं. सो इन दिस केस देयरफॉर आवर टोटल एनर्जी will be the sum of potential energy plus kinetic energy, right? So we are neglecting all sort of energies which are except these two, like vibrational, frictional, heat, thermal, जो भी रहेगी. तो according to conservation of total energy, considering a system of particles into some sort of ideal conditions, we say there is no loss of energy to the other forms of energies. I'll say the total energy of the system is always constant. It means if I have a body which is under a motion and it has some kinetic energy, of course it is in motion. So if I stop that particle, all of its kinetic energy will transform into potential energy, making the total sum remains the same, right? So this was the third conservation of total energy which I gave you as a homework, and you all know this already from your previous classes. This is not a very new thing, but this is a major conservation law which will be applying in further higher numericals or theories, right? So this was the conservation theorem. Now we'll start a famous and the most important mechanics of a single particle. Till now we were recapitulating the basics of the mechanics we did in earlier classes, but from here we'll start the actual subject, which is our mechanics, and we'll first study for a single particle and then generalize for a system of particles. So let's start. In the beginning, the first thing is, whenever I am saying a particle is under some sort of force, right? So this force is basically comprises of two components. One will be the external force which will be putting on the system or on the particle, or some externally stimulated force which is altogether is external. There is nothing which is coming from inside. So this is the first component, and the second component will be जो अंदर से आएगा. अंदर से कैसे आएगा? Internal forces कौन सी होंगी? The vibrational forces, Coulomb interactions, जो मेरा पार्टिकल होगा उसके जो मॉलिक्यूल्स होंगे वो आपस में एजिटेटेड रहते हैं. We all know that. उनके अंदर थर्मल एनर्जी होती है टेम्परेचर के कारण. They have this vibration energy due to the Coulomb's interactions. Two particles are repelling, two are attracting, and all sort of internal energies. So I'll say in general terms any force comprises of two components, that is, first is the external force Fe, and second is the internal force due to internal interactions of the particle, and this will be Fi. This implies that whenever I am saying F is equals to dP by dt, so that means the P denoting the momentum here is actually denoting the momentum of some ith particle of the system which we are observing right now. So this is the momentum of that particle under motion or under state of rest, whatever it is, and the force we are writing here is the force, the total force having both the components of external impact and the internal impacts, which is again acting on the same ith particle, and this particle will have the motion corresponding to this force. So I'll write P vector is the momentum of the ith particle which we are observing. So it will be Pi, right? Pi can be written as m into Vi, the velocity vector of ith particle. Pi can also be written as m dri over dt. Also m will be the ith particle ka mass. So from here, now this force will be F here will be the total sum of all the internal and external forces acting on the ith particle, right? So F को अगर मैं break down करूँ तो F vector will be F summation ij, where I is not equals to j to n particles plus the external force which is acting on the ith particle. This I over here was the internal. This is the ith particle, right? तो अगर मैं इन सब को एक जगह पे accumulate करूं तो I will get F summation I not equal to j up to n ij plus F external will be equals to d pi by dt, which again will be d by dt of mi into dri over dt. I will get this equation. Now we'll consider the Newton's third law of motion, which says every action has equal and opposite reaction. So suppose I am the ith particle and I have some jth particle. So according to Newton's third law, the force with which I am acting on the jth particle will be equal and opposite to the force which jth particle will impact on me. So in mathematical form I can write Fij vector will be equals to negative of Fji vector, right? And here we are summating all of these. So if I find the total sum of I not equal to j and ij starting from 0, or I can say starting from 1 to n particles, Fij, this summation following the Newton's third law will come out to be 0, right? So from here this whole of the component will vanish and my equation of motion from here will become F external acting on the ith particle will be equals to, taking the derivative inside, mass mi being constant, I will get mi d2 ri vector over dt square. We already find this expression in the previous classes in terms of position vector. So this is my equation of motion of the ith particle, but it is also the equation of motion of the center of mass, because if suppose ith particle is the particle which is at a position where the center of mass of a complete system of particles is lying, I will get the similar equation. So here we were considering a single particle ith which was surrounding by a system of particles, and we found the equation of motion for that ith particle. So taking the same analogy, the center of mass is the position where the complete mass of the system is appearing to lie, and I say suppose ith is the same position, ith particle की जो position है वो exactly same है, तो अगर मैं center of mass के terms में निकालूंगी तो मेरी जो ये equation of motion आई है, it will also be the equation of motion of center of mass. Therefore, this is one of the major results, and it is the equation of motion.